Week 11, Complications Continued, Part 3. We will review two problems. It's very likely you will see some variation of these questions on the final exam. In this question, you see the kick at different stages in the hole. If you remember Dr. Santos' slides from week 6, you might remember how the pressure at the shoe behaves. The peak in this graph corresponds to case 2, where the gas is just reaching the casing shoe. The pressure increases at the surface as the kick rises because we allow the kick to expand as we circulate. This is necessary to maintain constant bottom hole pressure, slightly greater than formation pressure. The pressure at the shoe begins to decrease when the gas starts to pass the shoe because the gas is low density and does little work. The reason it's maximum just before the gas passes the shoe is that we have a complete column of mud which is transmitting the extra pressure that we need to hold back the formation and to make up for the work that the gas isn't doing as it expands. That's why the casing pressure is higher than the drill pipe pressure, because the casing has the gas in it. Once the gas is just above the shoe, we see pressure relief because the gas isn't doing much work. That mud used to do work, so as the gas passes the shoe, the pressure decreases. Here's a question that we'll look at in more detail. Take a minute to read the question completely. The top of this slide has important information from the previous slide. We'll use this information to answer the question. You may notice some of the information on the previous slide is superfluous. Let's start by making a picture. Likely you will find the picture helpful, and whoever's looking at your work probably will too. Let's find our overbalance and determine how far the fluid can fall. We calculate the wellbore pressure with 0.052 times 10.9, that's our mud weight, times 9,000, that's TVD, to get 5,101 psi. Our pore pressure was given, and the difference is our overbalance, 187.2 psi. To calculate how far the fluid can fall, we'll use the overbalance, 0.052 times mud weight, times TVD, distance fluid can fall, and we get 330 feet. Now that we know the fluid can fall 330 feet before we take a kick, let's see how many stands it takes to do that. Let's expand our picture. As fluid falls, it falls inside the annulus and the drill pipe. That's because the drill pipe, even if it has a float, will allow the fluid to fall down and pass through the bit. The drill pipe's capacity is given, but we must calculate the annular capacity. Then we'll add those two capacity factors together. Remember, the outer diameter in the annular is actually the value that's the inner diameter of the casing, 8.681 inches. And the inner diameter of the annular is actually the outer diameter of the drill pipe, which is 5.0 inches. When we calculate the capacity of the annular, we get 0.489 barrels per foot. When we add the drill pipe capacity to the annular capacity, we get a total capacity of 0.667 barrels per foot. Now, to get the fluid volume of 330 feet, we multiply the 330 foot drop by the annular and drill pipe capacity to get 22 barrels. We get those barrels by pulling the steel volume of the drill pipe. This is the steel displacement, also given 0.0075 barrels per foot. Dividing the 22 barrels by the steel displacement, we get 2,935 feet, or 33 complete stands.